Very good morning, sir. Good morning to one and all. I welcome to the National Technology Center for Ports, Waterways and Coast, Department of Ocean Engineering, Indian Institute of Technology Madras, a national workshop on Chandrayan 3, importance, benefits and awareness before the soft landing in moon. I welcome one and all. Now, invocation, Tamil Thai Varthu.
நீராறும் கடலுடுத்த நிலமடந்தை கெழிலொழுகும் சீராறும் மதனமென திகழ்வரத கண்டமிதில் எக்கணமும் அதில் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு திரை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம்பியந்து செய்ய மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
Now, I request Dr. D. Kumaran Raju, Principal Scientist, National Technology Center for Ports, Waterways and Coast, IIT Madras, Chennai, to provide the welcome address.
Raju, you are muted, I think. Raju, you are muted.
Dr. Raju, sir, you are in mute. Yeah, please.
Distinguished guests, esteemed speakers, colleagues, ladies and gentlemen, good morning to you all. We all grown up with grandmother stories about moon, and tomorrow going to be a memorable day for all of us to feel proud to be the fourth country to soft land in moon, and especially the first country to soft land in this South Polar region. It is a proud and prestigious moment for all of us to mark this historical event, and also to mark this event, we wanted to conduct this workshop jointly with the Ministry of Port, Shipping and Waterways. Today we have three esteemed speakers for this workshop, and we wanted to extend warm welcome to all of them to share their experience and to make this day a remarkable day. With these few words, I welcome once again all of you and welcome again for this important and memorable workshop. Thank you.
Thank you so much for the nice welcome address, sir. Now I request Professor K. Murli, sir, Dean Faculty, as well as Professor Department of Ocean Engineering, IIT Madras, Chennai, to provide the opening remarks.
You are able to see my screen, Ganesh?
Yes, sir. Clear.
Yeah. Good morning to all of you. And we are very happy to host this workshop. And we are collaborating in this effort with the Sagarmala program of the Ministry of Port, Shipping and Waterways. And we also thank the ministry and the Sagarmala team for having helped us organize this workshop on the occasion of the Chandrayan 3 landing on the moon. And there is very little effort or very little research that has gone into the science of the moon as a celestial body, and therefore we thought we will capture whatever research that has gone into the celestial body in the country so far, and also some information about the technological side of the program, what the technologies which are directly involved and the technology which is also indirectly involved in this particular project and in the further efforts. So in this context, we have invited three speakers. One is Dr. Syed Makbul Ahmed, a principal payload scientist, XD Links Labs, Hyderabad, Telangana, India. He will be talking about the Chandrayaan 3 project, and yes, he will be talking about the preparations that they have done for any eventuality in landing and hoping for great scientific inputs. So this is the talk. This is the topic on which he is going to deliberate on. We will also be hearing from Mr. Leo, Principal Scientist, NTCPWC, IIT Madras, significant features of landing autonomy of Vikram lander of Chandrayaan 3 mission. And we will then hear from Professor K. Muthukumaran, Department of Civil Engineering, National NIT Trichy, Tamil Nadu. He has been instrumental in carrying out some key projects on the geology and structural part of the celestial body. So he will talk on lunar soil simulant for Chandrayaan missions. So he has been involved in the interaction of the rover and the interaction of the soil, interaction of the rover with the lunar soil and the geotechnical properties and aspects relating to strength and stability he'll be talking about. So with that, we will be winding up this program at around 12 o'clock. Just a brief introduction about Dr. Syed Mahbul Ahmed. He has a PhD. He is a trained physicist. He has a PhD from PRL Ahmedabad in 1990, and he has also an extensive training in UV spectroscopist. Worked in the areas of planetary atmospheric simulation experiments. Dr. Ahmed worked at DIE's Institute of Plasma Research, Gandhinagar, for 13 years. During this period, he worked for NASA JPL for 2 years and sabbatical at Swiss Federal Laboratory. He joined India's first moon mission, VSSC 2004, and built a commercial off-the-shelf mass spectrometer, which worked successfully, a first-time effort by any human being. A copy of the same instruments worked on Mars for 8 years, and another working on the lunar orbiter. Dr. Ahmed moved to University of Hyderabad in 2009 and worked here as head of the instruments facility for 13 years. Right now, Dr. Ahmed is conceptualizing hyperspectral imager on a CubeSat platform to look at the Earth. This will be the most sophisticated instrument packed on a tiny 6U CubeSat. A brief introduction about Mr. Leo. Mr. Leo has 16 years of R&D experience in maritime autonomous systems, marine instrumentation, and process control. Currently working as a principal scientist at NTCPWC IIT Madras, and also pursuing his PhD in autonomous shipping at the Department of Ocean Engineering IIT Madras. He obtained ME in Power Electronics and Drives at the College of Engineering Guindy and BE in Electrical and Electronics Engineering. He has recently developed an indigenous unmanned autonomous survey vessel for bathymetry applications and other surveillance applications in various water bodies. In the past, he worked as a senior project scientist at NIOT in the Energy and Freshwater Group and developed power takeoff systems for indigenous wave energy and vortex systems. He has also developed direct driven alternators for indigenous tidal turbines. He has also worked in thermal desalination systems, which use naturally available thermal energy in order to produce clean energy. He has a patent granted in desalination and 3 published patents in autonomous survey vessels, hydrokinetic turbines, and wave-powered navigation buoys. Finally, we will be hearing from Professor Muthukumaran. Professor Muthukumaran is currently a BA Chair Professor at National Institute of Technology, Tiruchirappalli, India. He obtained a PhD in Soil Structure Interaction and Marine Geotechnical Engineering from the Department of Ocean Engineering, IIT Madras. He has published more than 200 papers in international and national journals and conferences. He has completed 5 R&D including 2 Chandrayaan mission projects and 70 major consultancy projects in geotechnical engineering, and also created 2 patents, including moon soil as a patent, a method for manufacture of highland lunar soil simulant. He has guided 10 PhD and 6 PhDs are in progress, and he has also guided several postgraduate scholars. He is the founder chairman of Indian Geotechnical Society, IGS Trichy chapter. He has been elected as a member of IGS National Executive Committee for 2017-18 and 2023-24. He is a member of Technical Committee on Preservation of Historic Sites of the International Society for Soil Mechanics and Geotechnical Engineering. He has received DST Young Scientist Award, IGS Srimati Indra Joshi Biennial Award, and also Keynote Paper Award for GeoMate Conference 2015 at Osaka, Japan. He is an associate editor of Australian Journal of Civil Engineering and serving as editorial board member of several journals. He has received several awards, including Bharat Vikas Award and NIT Trichy Achiever Award for research publications, research projects, and maximum citation and consultancy projects. I mean, this is I introduce all the speakers upfront because this will set the context that we have the most relevant speakers in this part of the country for this particular workshop, and we are very happy and honored to have them here. So we will start with the first presentation from Dr. Syed Makbul Ahmed on Chandrayaan 3, prepared for any eventuality in landing and hoping for great scientific insights. Dr. Ahmed, please take over from here.
Thank you, Professor Murli. And I just like to thank the organizers, IIT Madras, and especially Dr. Sri Ganesh, because of whom I have come to this platform. This is a great opportunity to interact with people from various walks of life. I'm really excited. And I really look forward to giving this lecture. So I got roughly around 20 to 25 slides, and I expect to finish them within half an hour. And I would be very happy to answer any question post my presentation. So if you permit me to share my screen, I would go ahead and share my screen. I'm doing, thank you. And it's coming up. I go here, yeah, it's here, and hope it's, is my screen seen?
Yes, it's
Yes,
visible.
sir.
Please go ahead.
Okay, thank you, sure. Great. So, so roughly what I plan to do is I'm trying to spend most of the time on Chandrayaan 3 and in particular landing aspect. So a couple of 4 to 5 slides will be about how uniquely Chandrayaan 3 the people at ISRO have prepared for any eventuality, as I use the phrase, and that's what the chairman ISRO has mentioned. So most of my presentation, that is almost 50 to 70%, is based on Mr. Somnath's presentation, his lectures in the past 1 month. He has gone on record to give extraordinarily clear-cut explanation about how exactly we are going to land. And of course, the later part would be my part, where being an instrument scientist and having worked in Chandrayaan 1, I would speak about what these instruments are capable of. So let's start off. So this is the GSLV Mark III in a new avatar. They are calling Launch Vehicle Mark III. M4 is the version. And of course, no point in going into the details of the rocket. But I would just like to touch upon a couple of aspects of this rocket. And the first 3 slides are kind of a very popular level for the very young students who have joined. So the press called it as Bahubali. This is one of the very powerful rockets, GSLV Mark III. And this, please don't worry about 11.2. This is the escape velocity. It will go maybe half of around 4 to 5 kilometers per second in very little amount of time. And what it does is it carries 640 tons. And I want to put it in perspective, almost a huge trucks, 50 trucks of weight. And if you take the A380, which is the largest civilian aircraft, almost more than A380 it need to carry into the space. Just imagine the amount of thrust required for this, 4 times the A380 which you're seeing here. 4 times more superior, and stands almost 11 stories tall. Look at the perspective, almost 11 to 10 to 11 stories tall. You can see I just counted the floors. It's really goes up all the way. That need to be pushed right into the atmosphere, and it need to be put in proper orbit and all. It's a huge, humongous task on the part of rocket scientists in ISRO. Yeah, but I would not touch upon these. But I just like to show you just the nose cone, which is actually carrying the actual spacecraft itself is so large, 4 to 5 stories tall, and you put everything, assemble everything together, and you expect it to be gone into a perfect, they call it textbook launch. It requires enormous amount of experience, enormous amount of hardships, and anything, one particular one connector goes bad, your mission is all finished. Just one connector. They have few thousand connectors. They have few kilometers length of cables. So anyway, that's a huge task. So this is all what actually left for Moon, which is a propulsion module carrying the landing module. So these are the instruments. I'll come back to the about propulsion module, which has one instrument, one payload, and landing module has got 3 or 4 instruments, and rover has got the rover which is in the belly of the landing module, Pragyan rover. It has 2 instruments. So I would touch upon this in the last part of my presentation. Now, this is all. Everywhere at the bottom, I have given all the credit to Mr. Somnath, chairman of ISRO, who has the slides are all from his presentation. So he has gone on extreme details. I don't want to go into the extreme details, even though I have understood them. I can really discuss, but just well, since I got to finish everything in half an hour. So the mantra, the actual thing, we all, since I'm talking to the people at IIT Madras, it's guidance, navigation, control. The GNC, which is all a solid amount of work, which is going to work tomorrow. So what they are going to do is they have come up with fantastic guidance algorithm. Before you pay attention to this the table, please ignore this. So the very smiling way the chairman said that this time we are not trying to land successfully. Please listen to this phrase. He said that we are not trying to land successfully. Our mantra is to rule out, to mitigate every failure modes, and that's a huge task. What the chairman is saying that last time we tried to land successfully and they landed in trouble. And maybe later at the end of the presentation, if somebody asks the question, I'll tell you, if you try to land successfully, you can ask for trouble. Whereas solving every possible failure mode requires enormous amount of hardships, and they have gone through it. So they have gone through various things. So there is a sequencer which will take an algorithm. So it will run as per the algorithm. And there they have gone through thrust regulation logic they have put. They have made sure that the thrust should be regulated. Engine thrust perturbations, if they are taking place, they will take place. So they have made sure that even if the engine actually some kind of burping, some kind of noise and all, if comes irregular firing, they still said that we'll go ahead, no problems. Because if this you don't take care, and if it actually trips, then you won't be able to land. So they have accommodated huge amount of thrust perturbations, multiple mission paths. This is very important, where they have said that if everything fails, we'll still try to land. That is, there is a closed loop real time guidance which will be checking every aspect and making sure that it will land. If that doesn't happen, let's say if any violation takes place because of the engine going beyond the bound limits, then real time retargeting takes place. Real time, it will take place. It's all there program wise. Beyond the capability of real time, if that is also failing, they are maintaining a very good velocity, and they make sure that it's as if you have closed the eyes of a person. Still, it will go very happily, slowly, and in a constant velocity, it will land. So this is an amazing guidance control, where they are saying that no matter what happens, there's one more thing called anti-slosh. So anti-slosh is as if some drunkard person, a movement is also called slosh. So even if anything that kind of movements are coming, they said that they will take care of it. Now, I wish I could go into the details of all this. I would not bore you with all this, but I want to impress upon you the amount of the sensors they have plugged in. They have laser Doppler velocity meters. So they have velocity meters, they have altimeters. So they used to be only, of course, in Chandrayaan 2 also we had both laser based and then car band based. So various types of, this is kind of redundancy. If something doesn't work, then they make sure that what is the correlation between this and this. Make sure that if something fails, the other one should work as a backup. Hazard avoidance sector, they have huge amount of cameras, not one, more than one cameras, and then huge amount of program modes where they process and make sure that the path which they are following is in the right path and it will take them to a given target. And then inertial sensors. They have this fantastic laser gyro based inertial reference unit and accelerometer package, which has 3 to 4 sensors, which are state of the art. It's all built, and these are part of the landing module, which are eyes and a kind of other sensors in the landing module tomorrow. So just to tell you, so what exactly is the mission? You follow the real-time guidance bound check. Make sure that in real time everything is going smoothly. Any violation is taking place, let it take place. You actually deviate from there, and then it will lead to a real-time retargeting. So don't worry about the target which you're going after. Go for another retargeting. Let us say even there also you ran into retargeting problem also. Just don't worry, keep the velocity, the downward velocity standard, and as if your eyes are all closed, all sensors have failed, all logics have failed, but slowly descent journey, you maintain it in such a way that you're going to actually land. That is because you're maintaining a constant velocity. You're made sure that there is no sloshing, no drunkard kind of moving. I'm sure this will take you to the target. Yeah, little bit more. I hope I'm not boring you too much, but this is absolutely the numbers and various actual spot on issues which they have addressed, and they have made sure that this will work as compared to Chandrayaan 2. So as I told you, mitigate the expected failures, not to land successfully. Don't worry about landing successfully. This is the mantra. Instead of half kilometer by half kilometer target and successfully landing last time, which ran into problem, now they said that go for a better strip, which is 4 kilometers long and 2.5 kilometers width. Not one, there are 3 strips they have identified. So this is much easier. It's just like a huge the transport aircraft from the military landing like that. Illusions 76 and all like that, they can go and happily land. It is a sequence to tackle, as I told you, just sensor failure, engine failure, algorithm failure, and calculation failure. Just don't. These are the phrases I used from the presentation of the chairman himself. These are not my phrases. So it's all there. Land anywhere instead of a spot. Huge addition. Lot of addition has been made where the cameras, they have added one more extra camera. They have added one extra antenna to make sure that communication takes place in a robust way. Lot of solar panels, additional solar panels all around the lander, so that even if the landing takes place in an odd way, you are facing the sun and extracting good amount of energy to make your experiments go. And Doppler velocity monitor, very crucial sensor, just to make sure that constant velocity and everything failures, the DVM will take you happily to the spot of your choice. And then already a orbital high resolution camera has taken almost quarter meter very high resolution images. All those are plugged into the lander. So the moment the lander finds itself, it will know that which direction it is going and where it is expected to land, and that will help. This was not there in Chandrayaan 2. They have added 250 kilograms of extra fuel so that they can hover for very long, almost 1 minute, and that will help them very happily to avoid any kind of boulders or any kind of some kind of craters and all. If Chandrayaan had more fuel, in fact, that's what the chairman said. If Chandrayaan had more fuel, they would have maybe landed better, because they were trying to successfully land. In that pursuit of successfully land, they could not control the velocity and hence slammed on the southern pole of the moon. Well, this is just one more simulation they did. They did huge amount of simulations. I don't have that particular slide of Mr. Somnath, where they said that no matter from where they went, they made sure that I was telling you about the 4 kilometer long strip and 2.4 kilometer wide strip. So they said that I start from here, I start from different place, I make sure that I land in that flat surface, which is much longer and 2.4 kilometer width wise. All simulations done, they were all successful. And these are the places where last time they tried to land here. This is where Vikram lander in Chandrayaan 2 had an issue. Instead of that, you can see the strips. There are strips, many strips where near the South Pole they could land. And of course, Luna 25 also had booked its spot somewhere, maybe here, Luna 25, Luna 25. But anyway, I don't think we run into any trouble, and we don't even know where Luna 25 had actually crash landed. But these are our strips where we can go and happily land tomorrow. Now, crucial test they did. So I'm almost 30% through of my presentation. I got another 8 slides. So the crucial cold and hot test they did because of the following the ISRO's mantra. What is that? Seeing is believing. They said that, sir, we will do the test, sir. Then only we will say that we will things are working. What is it? Cold test. They assembled the whole Vikram and took it in a chopper, and all those 9 sensors I told you, all of them are put to use. Let's see that whether the velocity meters, altimeters, camera, they are all working. Is the camera trying hazard avoidance detection and taking it to the safer places? Camera working? Yes, the camera is working. Altimeters, all the altimeters test. I'll show you the pictures also, which the chairman showed. Hot test. What they did was from a huge crane, they let the Vikram lander actually to come down and simulated the weight also, which is 1/6 of what it is on surface of Earth. And they made sure that the engines are firing beautifully well. So this is like I give you a racing horse. Now the question is, can you control the racing horse? That's very important. 740 newtons is a huge propulsion engine. So they made sure that the propulsion is very, very nimble. It's like a very powerful horse, but you're listening to all your controls. They're throttleable, so that is your control, which is the leash is in your hand. 8 thrusters were tested for throttleable action, and the engines also. Vikram drop test was performed to make sure that the leg, which was actually about to take shock when the lander falls from few meters, so that test was done. One more very crucial was, once it is touched down, they have a sensor which will cut off the engines. If they don't cut off the engine, lot of regolith, that soil will be moving around, and it will spoil the solar panel and all. All those tests were done. Have a look at this picture. Seeing is believing. So this is the chopper in which all the cold tests were done. These are the hot tests where the huge crane made sure that the propulsion was done beautifully, the weights were all controlled. And then here is the drops test where they dropped it and made sure that the legs are working and the sensor cutting it off. Now, this is the last leg of my presentation. I'm talking about, I'll talk about the payloads. I don't have enough time to go into the complete greater details of these payloads, but this slide will give you a picture that how beautifully they have prepared. And this is the first time effort globally. Never it has been tried. First time effort globally. This is the first time on the moon, and this is also the first time on the moon. Otherwise, NASA has tried these two on planet Mars. So the ILSA is actually a moonquake measuring 3-axis measuring accelerometer, excellent resolution of 10 nano G, the G value, gravitational pull of the Earth, almost 10 raised to minus 9, minus 7, 10 raised to minus 9, minus 7 G resolution. Fantastic, built right here in India, starting from scratch. This is built right here. And Ramba is electron density, or the what are the charge, the dust which was actually caught on the astronauts and all in Apollo mission. They wanted to check in a region of almost 25 picoamperes equivalent current to 25 microamperes current. They also want to see how this dust, the charging is taking place as the sun rises and as the sun sets. First time, nobody has ever tried and ISRO on. So thermal conductivity experiment. So one sec, is there a problem? Okay, I think I'm very much in time. So there's a thermal conductivity experiment, which is also 10 centimeters. It will go and measure the thermal conductivity of the regolith, so that you can see, you can demarcate the inner aspects of the moon where you can see how exactly the thermal conductivity is taking place. There is a model which will help, and a gentleman who is speaking after me will be able to throw more light on this thermal conductivity. And then there is a retro reflector from NASA, which will help tomorrow Artemis program and all when they want to land. Rover payloads, fabulous payloads, first time never ever tried by ISRO, and they have a alpha particle X-ray spectrometer, which will actually it is in the rover. As the rover goes, it will actually shine the alpha particles, and then the material which is there, it will get excited, and depending on the fluorescence which is emitted, one can find out the sodium, magnesium, aluminum, silicon, all that which are kind of heavy in the periodic table. Then laser induced breakdown spectroscopy using a pulse laser would also give not only the heavy elements, it will give heavy elements, it will also give the light elements. So these are all being tried for the first time, and I must again emphasize, all are built here, indigenously built in India. Propulsion model carrying a shape instrument which is looking at the polarization properties of the earth, so that tomorrow when we are doing, we can look for exoplanets. And I think I'm running out of time.
You can
do I
take a
have
few
time?
minutes if you want. Dr. Ahmad, take a few minutes if you want, please.
Yes, sir. This is the last slide, sir. Last slide. So tomorrow is the showdown. What is going to happen tomorrow? This is a very beautiful, very nicely explained by Mr. Somnath, chairman of ISRO. This is his presentation. So what they are going to do is, they have the spacecraft is it's a power descent where the lander is hurling with a huge speed of 6,000 kilometers per hour. 6,000, roughly 6,100 kilometers per hour, which is 1.68 kilometers per second. So just multiplied by 3,600, you will get that number of 6,000. So they fire retro engines continuously, and then they end up at almost starting from 30 kilometers. They end up in 14 minutes. I'm sorry, in 11 minutes or so, 690 seconds. They will end up with a velocity which is again reasonably high, which is I've calculated 1,300 kilometers here. Now again, they hold the altitude, hold phase. They make sure that it will not stumble and all, but still try to retrofire and bring down the speed from 1,300 to almost 200 kilometers per hour at this stage. So from here, it is almost again retrofiring. Then from horizontal, they will by virtue of thrusters, they will make sure that it will be vertically above the lunar surface. Then it will have a lot of fuel to nicely hover for these many seconds, happily make sure that look for that nice strip and move around from point A to B to C, and then land on that beautiful 4 kilometers by 2.5 kilometers strip. And all the details which I explain, all of them are there. Plan A, plan B, plan C. Plan C fails, close your eyes, happily go and land here. That is what is going to take place. And imagine how terrible is the place where Chandrayaan 2 tried to land. We are going to land somewhere here only, which I showed you there. So it's just like the eagles are daring to land there. And thank you for your attention. Yeah, I'm all done.
Thank you very much.
Sir, Murli sir, you are muted, sir.
Yeah. So I have unmuted. Yeah. I'm happy if there are any questions.
Dr. Ganesh, you can take any questions, maybe a couple of questions from the participants if there are.
Okay, sir. We have a separate question and answer session just before the vote of thanks. Let us take it in that session. Thank you, sir. So now let us go to the second speaker. Now this is time for the speaker two, Mr. Leo. Now the floor is on yours.
Thank you, Mr. Sriganesh. Yeah, I'm going to share my screen. Hope everyone can able to see this. Yeah. So good morning, all. I'm going to talk about significant features of landing autonomy.
Leo, sorry to say, your mic got muted.
Am I audible now?
Clear. Go ahead.
Yeah. So Chandrayan 3 is one of the flagship programs of ISRO for the exploration of the moon. The mission is to demonstrate a soft landing at the South Pole to carry out the scientific experiment. The Vikram lander, named in the honor of Dr. Vikram Sarabhai, who is a visionary behind the Indian space programs. Since the orbiter for the moon is already in operation, no orbiter was launched for Chandrayan 3 mission. So with success, India will be the first to explore the South Pole of the moon. So this is the major specification of the lander and rover. So the mass of the lander when during the time of launch, it is 1,750 kgs around, and the power that can be generated on board lander is 738 watt, that is closely horsepower. Then this has got a sensor payload also, 3 types of sensor payload, and this has got the footprint of 2 meter into 2 meter. So the communication provided for the lander interface.
Leo, can you present in the presentation mode? You are still in the PowerPoint only.
Yes, sir. Yes, sir. So the communication link provided is through Indian Deep Space Network, IDNS, Deep Space Network, and the same can be interfaced also with Chandrayan 2 orbiter. So the major specification of the rover has got 26 kgs of mass, and this can separately after deployment it can generate 50 watts of electrical power. Then it has got the footprint of 917 mm into 750 mm. The maximum touchdown mass of the lander is expected to be 800 kg. The maximum landing velocity, vertical velocity, is expected to be lesser than 2 meter per second, and horizontal velocity of lesser than 0.5 meter per second. However, ISRO tested with a vertical velocity of 2 meter per second, 3 meter per second. The propulsion power on board lander is this has got 4 numbers of 800 Newton throttleable engines, and 8 numbers of smaller engines with a propulsion power of 58 Newton. So this has got the control system, engine control system, throttleable engine control system on board. So this is the designated landing site of the Chandrayan 3. This I have with the disclosed coordinate. I managed to get it from the Google Earth. So we actually learned, ISRO has got many lessons from the past mission, Chandrayan 2. So it was inferred that the Chandrayan 2 system was not adequately designed to foresee faults, to take corrective action, possible deficiency in throttling and the imbalance between the thrust produced by the thrusters on the fine braking phase and the hovering phases, possible communication data overload during the time of descending. Onboard sensor could not be able to provide precise measurement during the time of the landing. And the
Leo,
possible.
just a minute. Yes. Sorry for the interruption. I think your screen is not visible. That's the comment we are receiving in the chat box. Could you please one more time?
I'll reshare. I'll reshare it again. Yeah.
Leo, you may be just sharing the window only. You have to share your entire screen.
Yes, sir. I'll share the screen. Yeah. So now I'm sharing the screen. The Chandrayan 2's power system and its electronic components are malfunction due to the excessing radiation from the sun. So the improvisation taken in the next mission, actually after descent orbit insertion DOI, the below phases will be executed autonomously on finalizing the trajectory for landing. So there are multiple descending phases: rough braking, altitude hold phase, nothing but hovering, and the fine braking phase, touchdown phase, that is a terminal descent phase. the total descending duration is 15 minutes, lesser than 15 minutes. Then the horizontal distance during the time of descending operation is approximately 750 kilometers. Then the descending altitude, initially it was 30 kilometer, but we recently achieved 25 kilometer. So it has to reduce its altitude from 25 kilometers. So the improved features on the Chandrayaan 3 lander, there is a terrain relative navigation system that uses onboard cameras. There are multiple cameras already explained by the first presenter, and the lasers to map the landing area before descending. And also this will help to identify the obstacles as well. So earlier mission with first order poly guidance, the Chandrayaan 2 has got first order poly guidance. Now it was a little bit improvised to second order poly guidance that use TR and data, terrain relative navigation data to guide the lander to a safer landing spot. Then this has now got indigenous thrust regulation. So instantaneous thrust regulation. So it will take very faster regulations in the thrust. It is possible now. A backup landing system. If the primary landing system fails due to unforeseen situations, then the backup landing system present in the lander at present will take charge. So increased fuel capacity. So at present we have got a good amount of fuel to take up multiple plants during the time of descending. So we have now reinforced landing legs. We have got reinforced landing legs to protect the lander from the damage. These are all the lessons we have learned from the Chandrayaan 2 mission. So most of the improvisations are learned from the past mission. Then the lander communicates with Indian Deep Space Network, as I already mentioned. Then the Chandrayaan 2 orbiter also now is used for contingency link. So the onboard navigational sensors. So this was also already mentioned. So this has got laser inertial referencing and accelerometer package. Then the Ka band altimeter. Then lander position detection camera, lander hazardous detection and avoidance camera, laser altimeter, laser Doppler velocity meter, lander horizontal velocity camera, micro star sensor, inclinometer, and test down sensors. So the Pragyan rover, which is present in the lander, will be deployed after the successful test down. So the Pragyan rover will be controlled by the Vikram lander, which will send the commands to the rover through radio link. The rover will also have a limited amount of onboard autonomy to take care of collision avoidance when it is navigating in the lunar terrain. The constant supervision mission plan and of the rover is taken care by the Vikram lander. The Pragyan rover is significant technology achievements, and it will be valuable tool for exploring the moon. And this has got good amount of sensor payload for the scientific exploration on the moon once it is deployed. So the conclusion part, the lander is scheduled to touch down on tomorrow 6:05 p.m. Let's hope to celebrate its successful test down together. Thank you. Jai Hind.
Thank you, Leo. Thanks for this nice, wonderful presentation in right time.
Yeah.
And I now request Dr. K. Muthukumaran. I think he is just joined now. Actually, about his brief biography, Professor Murli has already given. I request Dr. K. Muthukumaran sir to take the charge. Sir, the floor is yours.
So Muthukumar, are you there?
Yeah, very good morning.
Good morning.
Am I audible?
Yeah, we can hear you.
Very good morning, all.
Good morning, Professor Muthukumar. Can you hear us?
Yes, sir, you're audible.
Yeah, you can go ahead.
Thank you so much for the opportunity. Let me share my PPT. I hope you are able to see the PPT. Is it visible? My screen.
Yes, sir. It is visible. Please go
Yes,
ahead.
sir.
Thank you so much. At the outset, I really thank IIT Madras for giving me this opportunity. We have been working for Chandrayan mission for the past 13 years. So for cover the entire research work what we did in the last 13 years in 30 minutes. Nevertheless, I try to complete focus on few important aspects related with lunar soil simulant and lunar structures. So my topic is lunar soil characterization and design of lunar structure for Chandrayaan missions. So myself, Professor Muthukumaran from NIT Trichy. So as the earlier speakers were talk about the importance of Chandrayaan mission, I'll briefly discuss about my role on this Chandrayaan mission and especially the lunar soil simulant and lunar structure. So I'm not very much going to touch about the other components, especially the interaction problem and structural aspects of uh, lunar habitations. So as we are all very well known, ISRO has already done Chandrayaan mission 1, 2, and we are expecting a very good news tomorrow evening for the third mission and many more to come in the near future. So there are several aspects related with this Chandrayaan mission. The foremost one, what we have considered is the interplanetary missions, where Moon will be taken as a transit place, where you can see that the first figure. So Moon will be acting as a transit place for interplanetary mission. So where Chandrayaan mission is having a huge potential to explore about the Moon surface and further development of Moon habitations, as well the launching pad for the futuristic mission towards other planet. So the first and foremost, we need to have a proper uh, interaction effect in order to have a very good lander stability as well as low rover mobility. As you have already seen about this lander Vikram and rover Gaganyaan, there are certain issues related with the moon territory, especially the environmental conditions. It's not as like our Earth territory. We are talking about very low gravity forces and a huge temperature variation, radiation, as well as subject to moonquake. So creating any moon-based structures, we need to consider all this environmental effect. And we do have a problem related with the materials to build a lunar structure. And the foremost task is based on the Chandrayaan 3 mission is how to utilize the institute resources for building such kind of lunar structure on the surface of the moon. So these are the major objectives of the present mission. So coming to the past missions, as we are all very well known, Luna and Apollo. So a few days back, we know about the instead about Luna 25 and Apollo is another mission from USA. And these are all the well-established missions happened for a few decades. And Luna's 25th, Apollo has already sent 17th mission. So we are in the right track. And in fact, we are doing much better than these two established missions of Luna and Apollo. So as in order to create this particular interaction study and the stability analysis and the possibility of constructing lunar structure on the lunar environment, artificially we need to create a lunar soil simulant. And many have already simulated, many countries have simulated such a simulants using rocks, ash, silt, sand, and mineral splashes. So we have also tried our level best to create a lunar soil simulant, which will be almost equivalent to the lunar surface. What you have seen, this is the one what we have developed LSS ISAC 1, which is almost resembling the actual lunar condition, especially in the highland. So basically, the lunar surface is divided into two zones, highland and marland zones. And what we are intending to get our lander and rover mobility mainly on this highland side. So we have developed a simulant using unauthorized rock minerals, basically to have a lander and rover stability and moon habitations related aspects. So we have also extended the studies related with the dynamic characteristics of the lunar soil because the moon is subject to huge moon fields. So let me briefly explain about the concept of the wheel-soil interaction. This has a two component. The first one, what you are seeing is the rigid terrain. The second one is the flexible terrain. This rigid terrain is as like our current road construction, where your road will be taken as a rigid body, and where you have a wheel, either it will be flexible or rigid. Mostly it will be taken as a rigid wheel. Whereas in case of the rover movement on the moon surface, this will be considered as different aspects because the surface of the moon is having a very soft material which is acting as a more flexible medium, where we will be acting as a rigid medium. So in the interaction, a response is purely governed by the syncage potential of the soil material. So especially the lunar soil, how much is going to have a syncage with respect to the applied load, that is the one going to decide about the interaction effect, and that is the one going to decide about the drag force, how much we need to apply on the rover. So the rover design is completely governed by the characteristics of the subsoil, that is the moon soil. So the moon soil simulation is very, very important to consider about the wheel soil interaction. So basically the interaction comes through this area, how much it is settled down or sinking on the surface of the moon soil. So based on that, the study has to be extended. So this is the basic principle. The rover mobility is basically a rigid body resting on soft soil, and the movement is happening on the soil. So this is a simple physics. What you are saying under the static condition, the expected resistance of mobilization is uniform. When you're talking about the mobility, the traction forces keep on changing with respect to the response of the soil. So as we know that the soil characteristics, the moon soil characteristics may not be same throughout the moon surface, and there will be huge variability. And this variability will be considered in the rover mobility, and that is what this particular study has undertaken to design a proper wheel soil interaction considering the syncage potential of the lunar soil. The actual lunar soil is a monophase system. It's not as like the three-phase system what we are dealing with the Earth. So it is completely taken as a single soil system. Considering the conventional soil mechanics principle may not be directly applicable to the moon soil interaction study. So mainly the study is extended with the terrain mechanics principles. So this is the actual lower soil profile. So if you look at here, our concern is very much on this depth of 10 meter, where we talk about aerolic material. So this 10-meter depth is completely governed by the characteristics of the moon surface, where we need to study about the internal characteristics of this soil, and where we are trying to build the structure, where we are trying to solidify the soil to make this structure suitable for any lunar habitations. So this soil is basically a very soft in nature. So we have a lot of difficulties, challenges to design the soil characteristics to such a way that which will be considered in the actual rover mobility study. So mostly if you look at this grain size distributions, the size of the lunar surface is always less than 1,000 microns, and majority comes under 140 microns seed size. It's predominantly consists of fine grain and fine silk particles. So thereby, so in the absence of water, the mobilization of corrosive resistance in the soil is almost insignificant, and predominantly the soil strength is governed by the frictional resistance. So Apollo mission has brought out almost 400 kg of rheolic sample that will be taken as a benchmark results for our analysis, especially the Apollo 16 core sample. So based on this Apollo 16 return sample, LSS are being prepared, and that has been validated with various engineering and physical characteristics of this LSS. So these are the properties given by Apollo 16 mission. So the first and foremost task is we need to map these engineering characteristics such a way that the soil which will resemble the lower ground. So it is decided to go for a highland soil simulator with the help of ISRO. And so basically this is the first identification of unorthodox rock locations. It is Periyar University under the Professor Unbelievable leadership. This was identified, and basically this identification is mapped as well as mapped in terms of mineral as well as the chemical composition of the material. That has been very well mapped with all the engineering characteristics. So the place is called Sitamuti near Salem. It was identified where the outcrop unearthed rock minerals are.
Sir, sorry, sir. Sorry for the interruption. So I think your PPT is not shared. It is not possible to visualize. Could you please share the screen one more time, please?
Thank you. Just a minute, please. I think it is. I'm not having the privilege to share. Somebody has disabled. Yeah. Is it visible now?
Yes, now it's visible.
Yeah, I'm on slide number 13.
Take your own time, please.
So this is identification of on that rock page. It was identified and that's been decided to have a different sizes in order to map the actual lunar simulant. So basically, we have gone with the 5 simulant with various gradations, and the average was taken, and it has been mapped with the chemical as well as the mineral composition of the rock. So these simulants have been further divided into various categories A, B, C, D. It is the percentage of brines, and accordingly, these brines are analyzed in the laboratory for engineering characteristics, and the pulverization process has been done in Salem with a very quality controlled manner. All the tests were conducted as per the total provisions, and all the test results have been mapped with the lunar upper and lower limit, and one which is very close to the expected lunar actual size sample has been picked up, and that has been further analyzed in the laboratory for various characteristics, strength as well as the physical characteristics. So what you are seeing in the screen, I'm just moving faster because I want to go a little more on the structural point of view in the later part. So this is the way the complete analysis was done, and based on this analysis, we have come up with ASS this unorthodox rock mass 2 is giving the properties very closer to the Apollo 16 sample. So based on that, a further analysis was done, and to get especially to get the sinking potential on the LSS developed envelope. So for that, we did several plate load tests. Based on the plate load test results, the modulus have been obtained, especially the deformation modulus and shrinkage exponential we are obtained using the simple paramechanics principle. Using that, all the other parameters have been obtained. So this is the final values what we have obtained with respect to the developed LSS ISAC-1, which is almost resembling the actual lunar soil characteristics. So based on that, the further characterization was done in terms of the dynamic as well. So using cyclic reaction apparatus, we have done the cyclic analysis. So just having a overall comparison about the lunar simulant. So what you are looking, the black lines or the boundary for lunar. Black line, what you are seeing is the lower and upper boundary for the lunar 16 black sample. And the other colors, what you are seeing is various simulant developed elsewhere in the world, which was compared with the LSS ISAC-1. You can see here the LSS ISAC-1 where the top is touching the lower limit and bottom is touching the upper limit. And middle is having exactly mean of the lower and upper. So that shows very clearly the established or developed LSS is having a mean characteristics of the actual lunar simulant, which is brought back from Apollo 16 mission. And moreover, the simulant what you have seen here, especially the very famous JAC1 developed by USA, are having a lot of uncertainty compared to the LSS ISAC-1 because LSS ISAC-1 is completely developed based on the natural material, unorthodox rock material. Whereas all other simulants have used artificial material like fibers, they have used glass beads to create the gradations to map the engineering characteristics. So our simulant is much superior than the simulant available elsewhere in the world because our simulant is completely decided, developed based on the natural material. And that is why the characteristics, engineering characteristics, what we have obtained is much similar to the actual characteristics of the lunar that was witnessed by the actual test, rover and lander stability test in the ISRO laboratory. And we have also done the microstructural analysis of LSS ISAC-1, and it shows that structure is non-muscular structures without any cavities, shows very good strength characteristics, which we extended with all other characteristics. And our simulant is very much close to the actual simulant than any other simulant available elsewhere in the world. So we have extended this study with all the relative density and strength characteristics using triaxial test and consolidation characteristics. Though water is not available, so during the time of mobility of a rover, rover weight can have a prolonged settlement on the lunar surface. So in order to estimate the prolonged settlement, it has been named as a consolidation settlement in lunar surface, and the consolidation characteristics also estimated using this laboratory. And finally, our LSS ISAC-1 as compared with the so-called very popular ISAC popular LSS developed elsewhere in the world. So this study has extended with the actual characteristics of the shear strength. The shear strength component is a very important component while we are considering the mobility of the rover. So we have considered the extreme conditions in the lunar environment. So one is the normal lunar terrain is having a relative density close to 63%. So that will be taken as the actual shear strength to mobilization with respect to the application of rover weight and rover mobility. The other extreme side is taken as when the lunar surface comes under the very soft compactness, it is taken as 30%. And if it is a densified state, it is taken as 80%. So for various relative density, with the application of the confining pressure, that is the pressure what we are considering application from the rover B, and how the shear mobilization is taking place along the surface of the lunar surface has been estimated using the triaxial apparatus, and that has been estimated for various. And finally, it shows very clearly that the angle of internal friction, that is the very important significant component with the wheel soil interaction stability analysis, comes around 38, 41, 33 with respect to loose actual state and dense state with respect to the lunar surface. And corresponding the value of measured cohesion value is almost insignificant because though the soil particles, lunar soil particles are comes under very, very fine. So in the presence of water, it has the mobilization of cohesion is almost insignificant. The study is further extended with the X modulus analysis for the actual lunar structural study. And we have developed a model for calculation of X modulus with respect to the lunar condition, considering all this 1/6 reduction modulus. The other important aspect with respect to this particular study is considering the moonquake effect. So basically, there are three major moonquakes expected, four kind of moonquakes expected in the lunar surface. Deep moonquake normally occurs more than 700 kilometer depth. Shallow depth is about 20 to 30 kilometers. And the thermal quakes, and moreover, introduced by meteoroidal impact. So the shallow moon quake and the meteoroidal impact quakes are very, very significant as far as the lunar structure concerned. Since there is no almost a low attenuation level in the lunar surface, so the moon quakes always keep on rings like a bell on the surface. So the attenuation level is so low, creates more issues to the lunar surface. And whenever we do the construction on the lunar surface, we should also consider the effect of moonquake resistant structure. So this is the history of these moonquakes reported by NASA. So the cyclic triaxial apparatus has been used to get the complete dynamic characteristics of the soil. And this table has given the complete picture about the dynamic characteristics, shear modulus and damping ratio with respect to various frequency, considering various confining pressure. This confining pressure has been taken with the interest of considering the foundation depth in the lunar surface. So the Bender element test was also conducted with the maximum shear modulus. So further, the study has been extended with the bearing capacity analysis. So the classical bearing capacity theory has been used, and the bearing capacity was calculated for various 1G condition as well as 1/6 G condition for the considered relative density 30 to 80. Based on that, the bearing capacity equations have been developed for the development. So this is the overall comparison about the bearing capacity for considering various simulant available elsewhere in the world with our lunar ISAC 1, LSS ISAC 1, evaluated for 1G as well as 1/6 G. This is the recommended limit of upper and lower limit of bearing capacity with respect to the footing size. And even you can see here, suppose you are talking about the astronaut standing on 1 foot. This is the required bearing capacity. So this is basically with the function of the surface area, how much it is going to be stressed on the lunar surface. So based on that, the required bearing capacity has been calculated. So basically, our simulant is simulant LSS ISAC 1 is giving in this range for 1/6 G and 1G, which is very much comparable with the results developed by the so-called very popular simulants like JSV, FSD, other simulants developed by NASA, developed by Korean, all developed by Chinese. Our results are much comparable, and in fact, it is much better than the results what it is available with other simulant. The very basic reason what I have highlighted, our simulant is basically a natural simulant, whereas the other simulants are having an artificial material like fibers and glass beads. Whereas these artificial materials will completely may not predict the actual behavior of the lunar simulant. That is why I'm emphasizing our simulant is much better than the available simulant. So the slope stability also extended with LSS ISAC 1, especially for the self-standing height, because this is very much important when you talk about excavation. So, I mean, in the future, we may have an excavation on the lunar surface to build the igloo kind of structure. So what will be the expected excavation depth without having any support? So that comes under self-standing height. So the self-standing height was estimated in the laboratory, and based on the laboratory estimated self-standing height, it has been extrapolated to the actual prototype scale. It says that the excavation can go up to 2 to 3 meters without having any support. The second important aspect in this study is emphasized about developing a building material using internal resources, because the construction material cannot be transferred from Earth to Moon. Transferring 1 kg of construction material will cost about 15 lakhs per kg. So it is not easy to transport the material from Earth to Moon. So we need to find an alternative material using the internal resources which is available in the lunar surface, or could be used for construction building material. So that study we have extended with using sulfur as the binding material, because the lunar surface is having abundant amount of sulfur that can be extracted, and extracted sulfur can be utilized, and the sintering techniques can be used to build a mold kind of structure. That is what we extended further towards the lunar structure component. So we used sulfur as the binding material, and it has been melted with the sulfur melting temperature close to 150 degrees centigrade, which is available in the lunar surface with our very hot temperature. So using the solar temperature itself, it can be melted and can write it required forms. So this shows the complete formation of lunar blocks using sulfur lunar blocks. The sorbine conductor is based on that. The optimum content of lunar sulfur content has been taken as close to 40% as taken as the optimum content for strength characteristics. So microstructural studies of this sulfur content improved concrete were being investigated, and further to check the complete temperature variation from very low temperature to very high temperatures, about minus 150 degree to 183, plus 130 degree, huge temperature variation with one lunar day. It's about the 14 days of Earth day. So the complete cycle have been studied with respect to the temperature variation with respect to strength degradation of the material. That has shown very clear picture that the developed sulfur content stabilized lunar blocks are having very low strength degradation, which is in terms of the weight loss, just a 3 to 3.5 grams for considering about 720 to 750 grams of weight. So as a whole, if at all we are planning to build a structure on the moon to have a lunar habitation, of course, it will be done maybe in another couple of decades. Because moon will be taken as an interplanetary point, it will be acting as a transit place to have other planetary missions. So astronaut has to stay on the moon. So for that, we need to build a lunar habitations, lunar structures. So basically, as we are all very well known, moon is having complete vacuum, no atmospheric air. So in order to have a comfort living atmosphere, we need to create a living atmosphere and build a structure. So essentially, the structure is subjected to applied force. So where we are creating atmospheric pressure in the chamber. So the structure is subjected to applied pressure. In order to counteract the applied pressure, either we can have a self-standing structure where the structural thickness can be increased in such a way that the force can be made at an equilibrium state. And for having such a thickness of this structure, we may need to spend more money and time to build a thick solidified structure. So rather, we can keep the structure as a thin and provide a foundation system such a way that the foundation system is subjected to uplift. So that is the concept of what we have developed related with the lunar habitation. So this is a complete dynamic characteristics of the developed sulfur modular with respect to the actual dynamic response considering the moon quake effect. I'll just move with a few more slides related with the structures what we have considered. There are different configurations developed elsewhere in the world, and ISRO also identified certain kind of structural composition, and this is the one conceptual layer plan for the lunar habitation. Partly the structure will be buried below the lunar surface, and partly it will be shaped as a igloo kind of structure at the surface of it. It's a very well-known fact that when you're having the dome kind of structure, the structural stability is much higher than the other kind of structure. So based on this conceptual design, we have taken as an analysis considering the uplift pressure, and when you are keeping as a minimum atmospheric pressure of 100 kPa, for that 100 kPa, for having a identified structure with this particular dimensions, what will be the expected uplift pressure that has been modeled, and that has been converted into model scale, and a model scale analysis was done in the laboratory, and uplift capacity was estimated in terms of two different aspects. So to consider the uplift capacity on the lunar surface, so we have used two components. One is a lunar coil, other one is lunar coil connected anchors. So when you are using lunar coil alone, the depth of the lunar coil effects is very larger, where considering larger depth of lunar coil is practically
So Muthukumar, we can't hear you. So Muthukumar, we lost your voice.
Am I audible?
Yeah. Now we are able to hear you. Yes.
Yeah. So in order to increase the uplift capacity, we have introduced both the low knot pile as well as anchor. The anchor will be connected at the bottom, so thereby the failure bridge has been increased. The resistance against the failure mass is very much increased. So based on this particular experimental study, we have finally proposed a low knot pile with the anchor as a supporting system for lunar structure. This is the experimental results with respect to the lunar piles. And here you can see the complete analysis with respect to various combination of the structures, considering various lunar structure, the corresponding accurate uplift capacity. So in order to get this uplift capacity, how much the lunar pile length and the lunar plate anchor needs to be decided. So these are all the lunar pile, lunar anchor plate all used based on the in situ resources material. So the same simulant, but it has been mixed with the sulfur, where the sulfur is melted with 1 degree centigrade, which is possible on the lunar surface, where we have a highly elevated temperature on the surface. So simple solidified procedure, sintering procedure will lead to have a solidified concrete kind of structure using the in situ resource of the moon. So this are the capacity finally. So the required sulfur content, how much the compressive strength that we are getting. And based on this compressive strength, you can select what will be the required foundation size on the lunar structure. So based on the developed simulant, ISRO has conducted the actual study, lower stability and land lower mobility and land stability study in the ISRO laboratory. So by the way, this setup is very simple and easy. So compared to setup, what NASA has is several times higher than what we have done at ISRO in terms of cost wise. So there are two. Am I audible?
Yeah, now you are audible, Dr. Muthukumar.
Yeah. So what you are looking on the left side is the lunar terrain. In order to consider that slope angle, you can see here it's a bridge kind of construction, but then the lunar simulant has been spread over that. So the lower will move even in the slope angle, the stability has been checked. So what you are seeing here is a helium balloon. So this balloon is being used to reduce the G level. So such a way that pressure has been applied at the top. So that will reduce the gravity force by 1/6. So thereby the lunar conditions have been simulated. And in order to have a high elevated temperature, what you are seeing is a halogen bulb, which will increase the temperature on the lunar surface as similar to the sunlight. The focal point can be changed according to the change in time, and where the complete response of the lunar surface can be easily picked up. So this is what ISRO has done, the complete rover mobility study on the lunar belt. So further, the lander stability study also conducted in the same simulant. So what you are looking here, the model of the lander. So the lander stability, as I already discussed about the function of the interaction between the leg and supporting soil system. So for various combinations, various angles, various inclination, various depth, various soil condition, that means the relative density of the soil from starting from 30 to 80. The various combinations that tests have been conducted according to the lander legs were designed in the ISRO. So in order to get the extreme environment, the extreme surface condition, so often the lander may encounter or the rover may encounter boulders and craters. So in order to get the stability against the boulders and craters, the model scale study we conducted in the laboratory for this is a drop height to look at the drop height, actual drop height. So modeled drop height with respect to the actual lander stability. So the lander is dropped to a certain height in order to create the stability. Suppose one leg is falling on the boulders, and what kind of stability is required to overcome the other legs when it is supporting on the loose brackets or soft landing side. So it's typically ISRO has done based on the similar what we have developed the LSS ISAT one. ISRO has done all the possible way conducting the test in the ISRO laboratory, and based on this systematic lander and rover stability analysis, so finally the rover and lander has been designed for Chandrayan 3 mission. Of course, these tests were conducted for 2 also, Chandrayan 2 also. So with that, I have come to my end of this project discussion. So basically, this is our ISRO Respond project, part of our Respond project research work. The title of the project is Detection of Lunar Soil Simulation for Evaluating the Design Criteria of Lunar Structures. So I would like to thank all these members, ISRO Respond team, and the current ISRO director, URS director, and the past director, and the team member, Dr. Venugopal, and Director Leos, Dr. K.V. Sriram, and Professor Anbal and his team from University. Meticulously, they did the LSS simulant, identifying the location and the gradation, pulverization, all was done by this team. And these are the team members involved in this project, Dr. Prabhu and Mr. Pisaga. So future mean colonization will be, India will be the pioneer in that area. So hopefully, maybe after a few decades, we may be able to see such kind of moon colonization on moon. So that I conclude my talk. Thank you. I'm sorry I was little rushed my slides because I have more than 100 slides. I want to show all what we did in the last 13 years related with the Mona soil, similar and the lunar structure. If you have any questions, I'm happy to answer. Please. Over to you.
So thank you so much, sir. Thanks for this nice presentation. Now the floor is open for 5 minutes question and answers for all the 3 speakers.
Shall I unshare my slides?
Yeah, please.
You can stop sharing, Professor Muthukumar. Yeah.
Yeah.
Participants can type their questions in the chat box.
Sir, I am Subramani from Bangalore. I have a question for Mr. Ahmed. Can I go ahead?
Please go ahead.
Yes, sir.
So good morning, everyone. It was a wonderful morning to have listened to 3 beautiful lectures today. And my question to Ahmed sir is, sir, how much time will it take for the Pragyan to come out of Vikram after touching down?
Yeah, this is not quite very well defined because what is going to be seen is as it lands, will there be some kind of hindrances? They will make sure that there is a camera which actually overlooks the outer ambience and all. So if all that clearance is all there, it may take a matter of hours or so. So it's not going to take too long also. But at the same time, it's not that the moment you land, the Pragyan would come out. That is what I believe, and that's what was discussed also a couple of times.
Yeah, thank you very much, sir.
Excuse me, sir. I'm Poonan here from Chennai. I have a small doubt about the lunar soil and the lander. So we have this vehicular activity going on, and there are some things that can cause a static attraction of soil particles on the wheels as well as on the instruments. How this can be prevented? Is there any electrostatic repulsion system or anything in place for our lander to overcome these type of adversities?
I believe the question is to me.
Yes,
Yes?
yes, sir. To anyone who is very much known in this field.
Yeah, to Kashna Muthukumaran, sir, please.
Yeah,
Yes, yes.
actually, that is what I emphasized during my presentation. Though the particles are so minor, in the presence of water, there will not be any cohesive force. The cohesive force, the one will always stick with the structure. So the lander, when it comes, I mean, when it resting on the lunar surface, though the particles are so smaller, it won't stick on the surface. So it will always govern by the frictional resistance. Uh, I mean, here,
Yes, yes, but there will be some static charges on the surface which can induce some sticking of these particles on the charged surface of the instruments, in case we are doing some XRD or some other type of uh, study, chemical or X-ray studies, or any charged uh, particle can cause between the Earth connection and the polarity changes.
okay, fine. As far as the mechanical characteristics, engineering characteristics of the wheel-soil interaction, there will not be any issue. But if you talk about the instrument which is available on the rover, probably I leave to the concerned expertise. They may have some sort of mechanism to have the periodical cleaning of the available equipment. I'm not sure about that. Could you please, concerned expertise, please enrich this.
Thank you. Thank you very much, sir. Thanks a lot. It's a very informative session. Thanks all of you and the organizers.
Thank you, sir. Now there is a question in the chat box from Sanchari Banerjee. Question to any one of the speaker. What are the criteria that are being considered while the landing site is selected? So I request Ahmed sir, you can able to answer this.
Normally, it has all been decided that we'll go to the South Pole. But considering the fact, especially even at the time of Chandrayaan 2, maybe Dr. Muthukumaran can make a point now also. But the primary concern is to go near South Pole, where a lot of activity is going to take place. Why South Pole? South Pole actually has got permanently shadowed regions where there is a contemplation that huge amount of buried ice from comets and in other foreign objects coming, and that can be frozen in the permanently shadowed regions of north and south pole of the moon, because the moon doesn't make a huge amount of tilt with respect to solar axis. And hence these craters, whenever you go to the pole north or south, there are so many craters where the buried ice could be present, and hence the south pole. Now, as far as the location is concerned, it was more of logistic and the way we one should land, and it was such a terrible time even to have 4 kilometer by 2.4 kilometer. I think that is the final factor. But yeah, I don't scientifically beyond South Pole, I don't see any other reason for a specific point.
Thank you so much, sir. Kasham Muthukumaran, sir, would you like to add any on this?
You ask me?
Yes, sir. Would you like to add any point to this one?
No, I fully agree with what Mohammed has mentioned. I think
Hello.
he's so, I mean, everybody is looking at the southern region. That's a very well-known pattern. They are expecting crystallized water molecule.
Sir,
And
this
three
is
more things behind that.
hello, sir. This is Jayaram from Comaco. So I have some question. I have some doubts regarding this advanced oil testing. Sir. I want to ask to Sir Muthukumaran, sir. Sir, you have yeah, sir. You have mentioned that amplitude of 2 mm and the parameter. I mean, what is the input parameters? How we are fixing the input parameters for dynamic soil testing? In Earth, that is different. In lunar, we have some different criteria to fix this protocol, right? So, in what basis we have fixed this protocol, sir, for Venn element and all this?
Yes, actually, bended element is the extreme case where we are getting the maximum shear wave velocity. Whereas we have gone with various, I mean, frequency. So this frequency content we have considered based on the existing literature. NASA has given a, I hope you might have already seen the lunar book, lunar source book, where you can able to see all these uh, lunar related studies done by NASA. Various people have studied and reported. It has been combined book where you can see the past moonquake data. In fact, one slide what I have shown in my presentation, it was given the past moonquake data for a period of. Uh, I mean, uh, NASA is claiming that they have done the measurement based on the instruments what they have used during the Apollo missions. So based on that, the input data given by NASA has been taken to the laboratory analysis. I hope you got the point.
Yeah, sir, got it, sir. Thank you so much, sir. It's really very informative, sir, to our geotechnical field. Thank you, sir.
Thank you so much for all the participants. I think one last question, maybe it has come in the chat box. What is mean by lunar day, sir?
Yeah, yeah, okay. Lunar day, yeah. So lunar day is actually just like sun rising and sun setting. So same thing happens on moon also, and it just so happens the way moon is oriented with respect to sun is that it will take 14 Earth days for these after the sun rising, and then 7 days to come over the head on the moon, and then another 7 days for setting. So it's just around 13.8 Earth days on which the sun will be available all around the moon, and hence the lunar day, if that is the question that he has asked.
Yes.
I hope Rahul might have got the answer back. So one last question, it came in the chat box. Let me just read it. Sir, I have curiosity to know about that if we have soil sample of moon brought by Apollo 16. So is it possible that somewhere I have read about that moon was the part of Earth? So somehow the same combination of soil we can match and verify the thing.
Uh, Absolutely correct. In fact, we got close to 1 kg of Apollo 16 broadcast sample for the validation purpose. Uh, in fact, what we believe that anatherosite rock sample what we have collected near Salem, probably the connecting point between moon and Earth, because it is having almost the same characteristics. In fact, NASA also uh, identified this fact and it has been informed to ISRO. Based on that information, the location was selected. So that is why I emphasized during my presentation. The simulant what we have is much superior than any other simulant elsewhere in the world because our simulant is 100% natural material, which is almost resembling the characteristics of the lunar surface. I hope I have answered your question.
Yes, I hope Mr. Anupam Kumar might have got the answer back. I think correct. So let us no more further questions from the participants also in the chat window. Let us go to the final session. This is the vote of thanks. Let us try to be in the last session. It is my pleasure to provide vote of thanks in this national workshop on Chandrayaan 3, importance, benefits, and awareness before the soft landing in Moon. This workshop organized by National Technology Center for Ports, Waterways and Coast, IIT Madras. Today, 22nd August 2023, between 10:30 hours to 12 hours through online. First of all, I would like to extend the thanks to the Ministry of Port, Shipping and Waterways and also Sagarmala for the opportunity provided to thank NTCPWC for organizing this national workshop. Next, I would like to thank IIT Madras Director for his immediate acceptance and permission to conduct this workshop on the Chandrayaan mission. Thanks to Dr. Murli sir, he is provided the opening remarks. Also, he given the introduction of today's all the three speakers. I would like to inform that Dr. Murli sir is a professor in the Department of Ocean Engineering. Also, he is a dean of faculty in the IIT Madras. He is also professor in charge for the National Technology Center for Ports, Waterways and Coast at IIT Madras. Through his constant support, also continuous support, this workshop was organized successfully within a short period of time. I would like to extend thanks to Dr. D. Kumran Raju sir, who provided the welcome address of this national workshop, also for his free hand for giving me to carry out this workshop in a well organized manner. Yes, it is also in a very short period. Next, I would like to extend thanks to all the three speakers, Dr. S.M. Ahmed, the first speaker of today's workshop, for his immediate acceptance to provide the talk in this national workshop and also deliver the talk within a scheduled time. Thank you, sir. Similarly, I would like to extend thanks to Mr. Leo and Dr. K. Muthukumaran, sir, the third speaker of today's workshop, for their immediate acceptance. Also, within a short period, they all committed and provided a talk on these Chandrayaan missions. And I would like to thank all the participants. Without them, the workshop may not be this much of grand success. As well as I would like to extend the thanks to all the faculties of departments of IIT Madras, as well as central government, state government employees, national institutes, major and minor ports, all the staffs, officials, many R&D institutes, people are joined, staffs are joined. I cannot name all the institutes' names because it's about more than 120 to 125 participants are joined from various institutes from throughout the India. That itself shows that the grand commitment as well as the success of this workshop. Thanks to all the technical and non-technical team who are directly and indirectly supported to carry out this workshop successfully without any technical problems. And at last, if somebody I missed, nothing is intentional. Thanks to one and all who helped for this successful completion of this workshop. At last, I would like to highlight one thing. As per ISRO's official website, the live landing of Chandrayaan 3 mission is scheduled to broadcast tomorrow, that is 23rd August 2023, starting from 17:27 hours of Indian Standard Time. Let's encourage all to use and as well as see the live landing to mark India's historic mission to moon. Jai Hind. Let us have a national anthem.
Thank you.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
we'll end this event. Thanks, one and all, for joining this event. Thank you very much.